Hi, everyone. Yeah, thanks for coming to my talk. And thanks for the introduction now. So I was talking about reliable learning under adversarial attacks. To give you some context, so this is based on two papers. One is called Robustly Reliable Learners Under Poisoning Attacks, which is a specific kind of adversarial attacks, which appeared in a Conference on Learning Theory 2022. And this is joint work with my advisor, Nina Balkan, Aubrey Blum, Steve Hanecki. The second work appears in NeurIPS 23, and it's an extension of these results to test time attacks, which I'll define, and distribution shifts. This is joint work with Nina Balkan, Steve Hanecki, and Rotana, who's also here. Okay. So in the first case, just to summarize what happens here, the attacker cares about specific errors. So this is the distinction from the previous settings considered in the literature. So I'll give some examples of this, but in contrast, the previous work considers average error on the data set. We are interested in adversaries, which are considered which are interested in specific errors. So they're interested only in errors on specific data points. Then we also identify exactly which errors can be defended and how. In the second work, we show that our work works for several different notions of test time robustness. And we give examples of good performance in linear and smooth classifiers. Okay. So to give you an intuition of this instance targeted poisoning attacks, which is a special kind of poisoning attacks which you're considering, suppose you have a recommendation engine which on Amazon, which gives you recommendation of products, and they're based on reviews. And as a seller, you might be motivated to add malicious reviews for competitors or just spurious good reviews for your own product. So people are usually interested in some specific instances that they want to attack, and they don't care about the average error, what happens on the entire data set. So the nature of the attacks are often better captured by this motivation of the adversary. Similarly, in automatic spam filters, maybe I only care about creating, poisoning your training data set so that my own spam messages get through, and I don't care about, all other different kinds of messages and what the average error of the spam classifier is. So I'll start with the formal setup of instance targeted poisoning attacks. So we have an instance space X, which could be your emails, images, so on. The label space we consider for simplicity binary classifiers. Again, it's easy to extend them to more classes and so on. We have data distribution over X times Y, and we have samples drawn from this distribution and instances, and the adversary is allowed to corrupt an eta fraction of these data points. So we have M XY pairs, X1, Y1 through XM, YM, and the adversary can corrupt an eta fraction of them in an arbitrary manner. So not just the labels Y, they can also corrupt the instance, the examples X themselves. Right, so the learner ultimately only sees as prime, which is the corrupted data set. And the goal is for the adversary is to cause error on X, which is unknown to the learner. So the learner doesn't even know which X is going to be targeted, but we want to protect basically all X in the instance space, or at least try to protect. Okay, so given a test point X, now we give it a definition of what a robustly reliable learner is in this setting. We want to give an accurate prediction, but we also give a guarantee of reliability, which is a certificate for correctness of our predictions. And the certificate is a real number. So it is basically a real value which corresponds to the adversary budget eta, for which the learner's prediction is guaranteed to be correct. So the adversary's budget is at most the second quantity that we output in addition to the prediction Y. Then we are sure that our prediction is correct. The learner need not be correct everywhere. So you also have the option to just output negative eta, which just indicates, I have no confidence on this prediction. But since you're forcing me to predict something, here's a prediction, but I have no guarantees on this. Hopefully this is not happening for most of the points. And for some test points, in general, predictions may not be certifiable. There are just, depending on how the distribution is defined and so on, there are points which you basically cannot certify. And finally, we have this eta, which we will call variously as robustness level, reliability levels, and so on. It's basically a measure of how secure the prediction is. So you can think of it as how confident the learner is Yeah, question?
Yeah, I just want to confirm that it's correct, as in like gives the right label, not whether or not the adversary was able to.
Yes, yes, that is, I'll come to that in more detail, but that's basically another distinction from prior work considered in this literature. Right, and formally we define robustly reliable learner as follows. So we have a target function f star in some concept in the concept space H. So there's a concept class from which we are trying to learn a predictor which maps instances to labels. And this is a standard realizability assumption. So we assume that there's a target concept in the class which correctly labels all the points. Again, we'll simplify this later on, but this is one of the starting assumptions which is easy to introduce the results for. The adversary has a fixed budget, and provided these two conditions hold, the learner is robustly reliable if for any corrupted data point S prime, for any test point X, it outputs a prediction and a reliability level with the guarantee that the prediction is correct whenever 1 and 2 hold. So whenever the budget is smaller than this eta that we are outputting, and whenever we're in the realizable situation, the prediction is guaranteed to be correct. And for any training data set, we also give an exact characterization of which points can be certified under this definition. Okay. And now I come to some connections with past theoretical work here. So there is this notion of nasty and malicious noise models. So it's been studied for a long time. The idea is the main difference here is the adversary is defined in as they change the data or the distribution, but the effect is measured only in terms of the average error. We don't care about prediction on a specific instance. The performance metric, which is used to design algorithms over, is just the average error over the distribution. Right. So again, we can have equivalent versions of those models in our setting where the performance metric is sort of modified. Then there's also a connection with the reliable useful learning literature where so that's the other guarantee of absolute correctness. So people, when we care about average correctness, they don't give a guarantee on a single instance whether it's going to be correct or not. They just give you a guarantee that on an average of the distribution you're going to perform well. But we give a guarantee which on any instance, we know whether or not we're correct or like how confident we are. And there is a literature which considers this similar setting. They also use the word reliable, which is introduced by Rivest and Sloan and was restudied as selective classification by L. Yaniv and Wiener. The idea is they don't consider adversarial settings, they don't consider attacks, and just normal unperturbed data sets. Can you be reliable? And again, the question there is, you want to be perfectly correct, but can you maximize the coverage of points in which you can actually predict while being certain about your correctness? Our certificate guarantees, and then this is the point that was just raised before, our certificates guarantee correctness, not just stability. And this is both in theoretical work and also this is prominent in the so-called certificates and the applied literature, where the idea is to guarantee that while the adversary perturbs, the prediction of the algorithm doesn't change. If it was incorrect, it stays incorrect. If it was correct, it stays correct. But we want to give this stronger guarantee of being correct whenever we give our certificate. Right. And a simple counterexample for this is, if a classifier just ignored completely the data and predicted positive everywhere, it would be perfectly stable because, it's trivially not going to change under any adversarial perturbation, but, it's a completely useless classifier. So just to give a simple example, we also want to give this stronger guarantee of being correct. So let me jump right into the algorithm that we have. So this is an algorithm which we propose, and this has the desired robustness guarantees. So a robustly reliable learner for any hypothesis class H does the following. Given a corrupted sample S prime and a test point X, it let's say there are two classes 0 and 1, so it finds a classifier which labels X as 0. So you fix the label of X as 0 and minimize the training error, and then you also fix the label of X as 1 and minimize the training error, and you predict the label which results in the lower of the two errors. And output a confidence level based on the higher error. So to give you an example with linear separators, suppose X is the point where we're trying to predict, and I want to consider a red classifier, which, suppose I want to try to classify X as red, then H red, let's say, is the best classifier, which predicts X as red and minimizes the error on the training data set. And H blue is the best classifier, which predicts X as blue and minimizes the training error. So these are the two classifiers in this case. Clearly, H blue seems to have the lower training error, and we can use this to compute both the best, both our label Y and the certification radius eta. The interesting property of this algorithm is it basically reduces to an ERM oracle. ERM refers to empirical risk minimization, which is a standard term which is used to basically an algorithm which considers a hypothesis class H, a set of classifiers, and minimizes on a given training data set the error among all the classifiers in that concept space H. Right. So we reduce to just two calls of ERM, which is in principle an expensive thing to do, especially if you have something like neural nets where you need to retrain them. So there are interesting further questions of making this approach more efficient. But at least this is an algorithm which achieves nice theoretical guarantees. Yeah.
I mean, there must be something about like efficiency or complexity that goes into this, right? Because like, is it the case that like an algorithm is correct if and only if it's this algorithm? Like, is this defining like what is the optimal output?
In a sense, yes. So we'll be able to show that this algorithm does give the best value of eta for all points. There is no algorithm which can give a better eta on any single point than this algorithm. So this is an optimal algorithm in that sense. Yeah, but then again, there is still this is all modulo computational like efficiency considerations. This is one of the algorithms that achieves the best objectives. Yeah.
How does that diagram relate to the statement on the mathematical statement on the slide?
Right. So in this diagram, we have a bunch of training points, two classes, blue and red, right? And we have a test point X. So we have the two linear, suppose a class H consists of linear classifiers, right? So all straight lines in this case. And we have, we essentially learned two different linear classifiers. One is H red, which forces X to be red and minimizes the error on this data set constrained on X being red. So yeah, let's say this has error 3 on the training data set, but also manages to label X red, and then there's H blue, which manages to label X blue. So these are the two H0 and H1 in the.
So H blue would have no error.
Yeah.
It make X blue with no error, but H red
will have error 3.
has error.
Yeah, basically. Yeah. And yes, this will translate to, I'll give some more intuition as I dive into why this algorithm is correct for how the second part works, but this is actually at least how the algorithm functions. Yeah.
But I guess if you have an ERM oracle for H, is it clear how to use that oracle for this? Because now you want to like constrain H to output something at some point, and that changes the class, and then maybe you don't have like an ERM oracle for this.
So we have the same, we're talking about the same H, right? So we assume we have an ARM oracle for H, and all we do is just modify the training data set such that X is labeled 0. So we just swap the label of X0 and on that modified. Yeah. Okay. So now we want to prove some guarantees about this learner. So how effective is the learner? And analogous to the coverage or usefulness guarantees in the literature, for reliable learners, we define in the robust setting what are the usefulness properties. So the robustly reliable region for an observed sample, S prime, so S prime may be corrupt, is defined as all those points in the data set where the learner outputs a threshold, a reliability threshold eta hat, for eta hat at least. So wherever the threshold is at least eta is the robustly reliable region with the confidence eta. So the robustly reliable region is a function of the data set, the learner, and the threshold. And for each value of threshold, you can define the set of points for which the learner is confident that, as long as the adversary's budget is at most eta, so I actually output a confidence level greater than eta. So we are sure that we are going to be correct. And for uncorrupted samples, similarly, you can define X as all those points for which, for all possible corruptions, so all possible eta corruptions of the uncorrupted sample S, the learners will predict on S prime the corrupted sample. It will give a reliability threshold eta hat, which is at least eta. So these are just, subsets of the data set. They are sort of monotonic subsets of the data set, which change with eta, which changes the function of the threshold eta. And given the data and the corruption level, we are interested in answering the question, what is the largest set of points the learner can certify? All right, so our first result says that the robustly reliable region of the learner that we proposed contains this set of points which we call the agreement region of classifiers with error at most 2 eta on the sample S. So what is the agreement region? So let's explain this with the linear classifiers. So agreement region basically is, so suppose you have all the classifiers, you consider all linear separators on this, let's say passing through the center, let's say that's our class. And suppose we consider all those which have error at most 2 eta. So let's say eta fraction corresponds to 1 point. So we consider all linear classifiers which have error at most 2. And we consider the agreement region, which is basically this gray region where all of those classifiers would still agree, would make the same predictions, right? So it's basically the complement of the set where there exist 2 classifiers which satisfy this low error property, but disagree on at least one point in the data set, right? Okay. And interestingly, this is a tight characterization in the sense we also show that for any hypothesis space H, any robustly reliable learner L prime, the robustly reliable region will always be contained in the agreement region of classifiers with error at most 2 eta. And I'll give intuitive proofs for these. The nice thing about this result is pointwise optimal characterizes this, what's the maximum amount you can certify under our definitions. Right, so yeah, there's also the question of how large the agreement region is, and we'll give some examples of how large this is. But I'll come to that. First, let me start with the proof for the upper bound. So the first thing we observe is given a Poisson sample S prime and test point X, the learner outputs the largest eta such that X is in the agreement region of classifiers with error at most eta. So this observation can be verified using, let's say, the example that we just saw. So we want to output the largest value of eta such that X is in the agreement region of classifiers with error at most eta. And the intuition here is, yeah, so if so we are essentially, by definition of the fact that H is minimizing the training error on these the 2 classifiers 0 and 1, it implies that if there was a classifier which was, yeah, so we want to make sure that the error of all classifiers which have error at most eta, X is in the agreement region, and in this example, X would be only in the agreement region of if we reduce eta even by, so that's why we have this 1 by m term there. It just says if it was eta was slightly larger, then it would not be in the agreement region of these red and blue classifiers, right? In other words, we want to find the so if we, for example, if we are allowed to corrupt only 2 points, then the adversary in this case then X would not be in the agreement region and would not be able to certify X. Then our learner is also robustly reliable. So using this observation, we can conclude that if we output Y and data and the concept belongs to H, then S prime was corrupted by an adversary with budget at most eta, then error because the corruption was at most eta and F star was assumed to be perfect on the uncorrupted sample, so its error is at most eta. And since X lies in the agreement region of classifiers with error at most eta, it must also agree with the correct target hypothesis F star, and that's why Y must equal F star. The robustly reliable region of our learner, the final conclusion is that it contains all the points in the agreement region. And this is also a simple proof by a triangle inequality. If S is poisoned by an adversary of budget eta to obtain S prime, X would be in the, and we also know that X is an agreement region of points with error at most 2 eta. This implies that on S prime, X is in the agreement region of points with error at most eta. And then this implies that it is again classified with robustness level at least eta. Okay. And to measure how large this agreement region is, so we have characterization in terms of this abstract agreement region, but on real examples, can we measure the size of this agreement region for H, for d-dimensional linear separators, and for certain nice data distributions, which we can show that for sufficiently large data samples, the robustly reliable region is almost 1, and it goes close to 1. Well, it is shorter than 1 by this eta times root d term. So by nice, I mean isotropic log concave distributions. And the nice thing in this case is that L can also be implemented efficiently, which I'll also talk about building on seminal work of Avasthi, Balkan, and Long. Right, so yeah.
Why should I feel like the regime as being close to 1? Like, is eta like 1 over d for some reason? Like, is that a good regime?
Yeah, eta 1 over d is definitely, well, like for large d, that's where you'll have, again, a good amount of, yeah, you have a high probability mass on the points which are reliable, right? Yeah. And as long as eta is like significantly larger than root d, we can be sure, sorry, significantly smaller than 1 over root d, we can be sure that we are very close to certifying all the points in the data in the space.
So like eta is like a measure of robustness, or sorry, it's the budget, right?
Yeah.
Why is the budget shrinking?
Yeah, so the budget is so the inherent difficulty in this problem is like how the in the isotropic log concave distribution, how the probability mass concentrates closer from any concept space H star. So there is a concentration, you can say that, within if your agreement region, if your budget is small enough, or your agreement region corresponds to a small enough radius, then it would contain enough probability mass, and that scaling is basically measured by this inequality. So right. So in general, we don't actually even have ERM oracles for linear separators. So the question of implementation still remains, even if we have this guarantee of high probability mass, of high, of reliability being certified on most of our points. Can we actually efficiently implement this? So we are able to do this in a slightly weaker model, where we are able to do this at polynomial time. So yeah, suppose the points which the adversary gets to corrupt are chosen randomly. So in this case, each point is selected with probability at most eta, and if it's selected, the adversary gets to corrupt it, otherwise not. But once the adversary gets to corrupt it, they can change both x and y in that point. So in this weaker model, intuitively, you can think of the adversary can only inject the bad points here. They cannot remove data points because, with probability 1 minus eta, you are going to get a random sample from the true distribution. Yeah, so in the previous model that we're considering, we had both addition and removal of points effectively. Right, so to define a robustly reliable learner here, we don't use the one that we defined before. We use a deterministic version of a previously proposed learner from malicious noise. And we show how to obtain output the robustness level there and obtain this reliable prediction. So we want to output the largest value of eta for which X is in the agreement region of classifier. So that's the intuition we had. That's the same intuition we had for the previous learner in the property which allowed all the upper bounds to go through. But in this case, we assume the error is at most C times eta for some constant C. And we cannot efficiently, the implementation challenge is we cannot efficiently check membership in the agreement region. So what we do instead is we certify a subset of the agreement region where membership can be computed efficiently and show that that subset has a large probability mass. Right, so the key observation here is that for any alpha learn classifier with unit, and suppose we learn the unit vector WH, then the agreement region contains this simple region, which is an intersection of a ball around the origin and this margin, also a margin around the learn classifier H. So this region, we show that this is guaranteed to be contained in the agreement region. This is easy to compute and pretty much recovers most of the probability mass. So in that sense, it's gets us, we are able to get the same asymptotic guarantees of 1 minus O root d eta here, but we're also able to compute this efficiently. And quick reminder, so of how our results compare to previous theoretical work. So we do certify correctness, not just stability under adversarial interventions. We handle isotropic log concave distribution. So prior work which give the stability certificates have only considered uniform distributions. Our algorithm is polynomial time. Again, previous works have only mostly considered ERM oracles and so on. And in this, for this result, we again provide a near matching lower bound. So the gap between the upper and lower bounds is in some constant factor in the radius of the agreement region. We show that no robustly reliable learner can certify eta outside of agreement region, which is of a ball around H star, which is roughly radius eta. We also, so far we've considered what if we have access to samples, what if our samples are coming from a distribution. Again, it's straightforward to use classical results from learning theory to extend our results to the distributional settings. So suppose the sample S was coming from some distribution and then the adversary gets to corrupt it. Suppose the size of the sample is at least d over epsilon square, where d is the VC dimension of the concept class, then the robustly reliable region in this case is contained in the agreement region of this is just a slightly smaller radius than what we saw before, 2 eta minus epsilon instead of 2 eta. So as the size of the sample grows, we can basically recover the 2 eta in the optimal, one of the best possible guarantees. And again, here is a near tight lower bound as well. So there's only slight looseness in this result as well. For any robustly reliable learner L, if we're sampling S from some data distribution D, then the probability mass of the points in the reliability region, robustly reliability region for L can be at most this agreement region of plus some small terms. So again, I haven't included all the details here, but feel free to check them. Now I move on to an extension of this setting, which is an active learning setting here. suppose the labels are expensive and the learner now must also select which points to label. So we know we no longer get X, Y points in our data set. We get, we suppose we get points sequentially, we get each X, and the learner chooses whether or not to request for the label Y. And in this interactive setting, the adversary can still choose to corrupt eta fraction of the labels as well as X that we receive. So the question is, can we still give a robustly reliable learner? Yeah, so we have interactive querying. Yeah, so the goal is to reduce label requirement, which is, the whole goal of active learning. But this makes it much more challenging, especially if the attacker has access to the learner's internal randomness, and they can decide how to poison based on how the active learner is going to choose because we assume the attacker is able to see which points we're querying. But our positive results are that active learning can help in the sense we retrieve pretty much the same robustly reliable region as in the passive setting, but at the same time are able to reduce the number of labeled examples that we need to achieve the same reliability, provided a certain property called the disagreement coefficient is small, which is standard in the active learning literature, but I won't have time to go into. So yeah. And the algorithm here is also pretty simple and intuitive. So for any new point, we will query its label if and only if it lies in the disagreement region of all classifiers that make at most a time mistakes on previously queried points. So we want it to be consistent, but it's possible that the adversary has corrupted up to a time fraction of the points that we have seen so far. So we restrict our attention to the agreement region of classifiers which make at most a time mistakes, and those are the points that we are able to that we query, and our reliable learner which we output at the end of the querying is the same as the learner which we had in the passive setting. Another extension that we're able to provide is to the agnostic setting. So remember, initially I made this seemingly strong assumption that F star, the target concept, lies in the concept space H, but in general, there's maybe no classifier which achieves perfect or zero error on the data that we observe. So what can we still get reliable learning in this setting? And turns out we are able to, and the reliable learner in this setting is defined to be a learner which agrees with every low error hypothesis. So there is some hypothesis which has some minimum error, and we want to guarantee that every low error hypothesis agrees on the points that we are able to certify. So we can still do near optimal robustly reliable learning in this setting. So the result which we have looks like this. So if the minimum error over the distribution is some new star, and number of samples, data samples is at least d over nu star square, then we show that there is a 1 minus gamma probability, and this 1 minus gamma probability term just refers to the requirement that suppose we're sampling over the distribution. So 1 minus gamma of the times that we sample S from distribution D, we guarantee robust reliability, in gamma fraction of the time we give no guarantee. So yes, this is an average over the sampling of S. Yeah, so we have 1 minus gamma probably nu tolerably. This just refers to the agnostic setting that the minimum error is nu star. We have a robustly reliable learner such that the probability mass of its robustly reliable region is again this term which contains the agreement region of classified with error at most 2 eta plus 3 nu star, where nu star was the minimum error of the classifier. So again, we are able to, as long as these nu star and eta are small, we are able to give good enough reasonable guarantee on the size of the agreement region, or the size of the probability mass where we're able to predict reliability guarantee of eta. And again, we have a corresponding lower bound as well. So there is some gap in this case. So we have a lower bound. There's a gap in terms of the new terms, which we have an agreement region of 2 eta plus nu minus epsilon as the probability mass of the which we show that any robustly reliable learner which satisfies the definition must have probability mass of its robustly reliable region at most this. With that, I move on to the second paper, the test time attacks, which I'll cover somewhat more briefly. So we study in test time attacks the differences. So suppose previously the adversary was able to change the data that the learner was using to classify, but now the adversary is able to change instead the point X on which we are making the prediction. So how does that change the setting? The notion of robust reliability changes somewhat in this case, but it also depends on how you define robustness. And there's a few different definitions in the literature, depending upon whether the attacker is allowed to change the true class of the label. So, your test point X, if it's, let's say, a cat or a dog, so is the attacker allowed to change a cat to a dog, or it can only maybe fudge up or add some pixels to the cat and still remains a cat? So can you change the true class of the label? But also, there's another question, if it does change the label, do we want to predict the original class or so if it changes a cat to a dog, are we correct if we are correctly able to predict that it's a dog now, or we are hopeless? If it's able to succeed in changing the label, then we just say, we're making an error. So there's several different definitions, and these lead to slightly different notions of robustly reliable regions. Yeah, just to give a concrete example, there is the stability loss where, so suppose there exists a perturbation Z of your test point X such that H of Z is different from H star X, then the adversary is said to have succeeded in its attack. So the adversary's goal is to perturb your point X to a point Z such that the prediction of my classifier H is different from the true label on the original point X, right? This is just one of the examples, and then with all the combinations, you can get slightly different examples. Again, so we can define a robustly reliable learner in this setting, which outputs a concept, a hypothesis H, and a reliable radius R. Again, the reliable radius is something that we're able to define for specific classes of adversarial attacks. So, for example, a commonly studied adversarial attack is a metric ball attack or LP norm attack. So you have the adversary has a budget of perturbing your test point X to within some metric ball of radius R around the point itself. And then we want to give a reliability radius R, which essentially captures this adversarial strength. So it is a guarantee that provided the adversary corrupted within R of Z, then the loss as we defined is going to be 0. So in other words, we are going to be correct and the adversary does not succeed in this case. So again, it's a correctness guarantee that we actually guarantee the prediction is correct. Again, we can extend the definition of the robustly reliable regions. We've already shown this. Can go a little faster. So again, it's robustly reliable region at the reliability level eta is the set of those points where our learner gives a value of at least eta as its reliability level. And again, the learner can always abstain by setting negative values of R. Obviously, this is not useful. We don't want it to happen too often. We want to maximize the points. Again, we want to give the largest value of R wherever possible. And again, as with poisoning, we obtain point-wise optimal guarantees for several different robust losses. So stability loss is one of them. We have 3 other different definitions depending on combinations of how you define what classifies as an adversarial success. Another interesting notion that's relevant in the test time attacks specifically is a safely reliable region. So these are the points where we give a reliability level of eta prime when the adversary has power eta. So this depends on both eta and eta prime. So adversary, by using its radius of corruption eta, it forces us to reduce our confidence to eta prime. So what are the points where we'll still be able to give this kind of eta, at least an eta prime guarantee? Right. So again, we are able to show safely reliable region for is large for linear separators under isotropic log concave distributions. We're also able to give these results for smooth boundary classifiers under smooth distributions. In the case of linear separators, the nice thing is we again have a computationally efficient algorithm. So this is just a quadratic program. The idea is to, in this case, the reliability level that we predict is the closest point that we have in the disagreement region for the point for a given point. And this is given by a quadratic program here where for any two linear classifiers which disagree, what's the closest point z prime to a given z that we observe in practice. So such that they classify x, I, y, I correctly on both the samples. They agree on the entire sample, but they disagree on z prime. So with that, I can summarize all the things in the talk. So robust reliability is desirable against instance targeted attackers. So, especially when you have like crowdsourced data or user data where people have particular motivations for classification on misclassification on specific points, but they don't really care about average data. So you expect a certain kind of attack. Then depending upon the concept space, the data and the corruption level, certain points are uncertifiable. That's kind of like lower bounds that we are able to show, but the nice thing is we have pointwise optimal algorithms in the sense whenever it is possible to certify, we are able to certify. And the nice thing about a robust reliable learner is they we're able to combine test and training time attacks. So there's a nice way in which they combine together, and which is one of the things that's missing in the literature. They work for both test and training time attacks. They are pointwise optimal. They give an exact characterization of the points that cannot be certified, and we are also able to handle more challenging settings where the active learning setting where we don't need all the labels, and we try to minimize the number of labels used at the same time as trying to be robust and reliable. Finally, whenever no perfect classifier exists, we have weaker robustness guarantees, but again, they can be characterized in terms of the agreement region. Okay, that's all in my talk. Thank you. Any questions?
Was there something like the algorithm to classifiers that can interpolate?
Interpolate what?
Like the basic algorithm basically says, take the point, pick and then pick a hypothesis and compare to hypotheses, depending on whether that's going to be able correctly or incorrectly, based on their for training, right?
Yeah.
But like many classifiers in practice will be able to perfectly fit that point regardless of label and have zero training.
Right. The challenge with the extremely flexible these concept spaces is that the agreement region tends to be really small. So again, that's in a question of can we come up with assumptions under which the agreement region is also reasonable. The algorithm itself will still work, but it's not clear if you're able to do something like, as you say, for any corruption, like for X, you label X as 0 or 1, you're still able to perfectly fit the data, then the issue is the agreement region is essentially not going to be empty, because
Right, I mean, Ada will be, like, the Ada UFO will be, right?
yeah, I mean, so in that case, the result will be kind of vacuous, because yeah, that's the best you can output there. Yeah, but at least even for the cases, so the nice thing is that in the second work, we're able to show for smooth boundary classifiers. So as long as the boundary is smooth and there is an assumption on the smoothness of the distribution, our results extend. So as long as I mean, if you have absolutely no constraint on the classifiers, then again, our results do imply that it's hopeless. But yeah, even some reasonable assumptions, like the boundary of the classifier is smooth and the distribution is also the probability distribution function is a smooth function, we're able to give these guarantees. Yeah.